This is second and final lecture of chapter 15, multiple integrals. In the previous lecture, you learned about double integrals. In this lecture, you will learn about triple integrals. So definition of triple integral I have already explained in the previous lecture. Here, we will practice many different types of problems. Those will explain you the solution procedure of triple integrals. So first see this example where limits of x, y, z are already mentioned in the problem. Triple integral of e power x plus y plus z dz dy dx. It is understood that these are limits for z. Z varies from 0 to x plus y. 0 to x are limits for y and 0 to 1 are limits for x. Okay. So as you did in double integrals, first solve the innermost integral by considering the variable z. Means put a bracket on the innermost integral. Means integrate this function with respect to z, treating x and y as constants. See what we get. Integration of e power x plus y plus z with respect to z, treating x and y constants is e power x plus y plus z. Limits of z are to be applied from z equal to 0 to z equal to x plus y. See what we get in the next step. Upon limit z equal to x plus y, you get e power x plus y means 2x plus 2y. Minus lower limit z equal to 0 means e power x plus y. Now you see you have integrated with respect to z. Now it is a double integral in xy, and this kind of problems you have already done. Okay, so you can solve it further yourself and see what is your answer. It's a double integral problem now. I'm writing the answer. Do this exercise yourself. 1 over 8 e power 4 minus 3 over 4 e square plus e minus 3 over 8. So after doing the calculations of this double integral, you should get this answer. If you get something different, let me know. Okay? So solution procedure of triple integral when limits are given, you see it's very simple. First solve the innermost integral, treating other two variables as constants, and then it reduces to a double integral that you can solve as you did earlier. Okay? Now let's consider a problem where limits are not given, rather region of integration is given. Means how to decide limits in a triple integral when region of integration is mentioned. Solve this triple integral. Dx dy dz over x plus y plus z plus 1 whole power 3 over a region D, where D is the 3D region bounded by x greater than equal to 0, or given by x greater than equal to 0, y greater than equal to 0, z greater than equal to 0, and x plus y plus z less than equal to 1. Okay. B is the region given by these four inequalities. What does it mean? It is the region bounded by x equal to 0, y equal to 0, z equal to 0, and the plane x plus y plus z equal to 1. By the way, what is x equal to 0? YZ plane, y equal to 0, zx plane, z equal to 0, xy plane, and this is also a plane. So the 3D region bounded by these four planes. Can you guess the shape of this 3D region? It is a special shape given a special name. XY plane, you understand? YZ plane, ZX plane. This plane, x plus y plus z equal to 1, meets x-axis in which point? 1, 0, 0, y-axis in 0, 1, 0, and z-axis in 0, 0, 1. This is oblique plane. This plane is not parallel to any of the coordinate planes. So it intercepts in these points. After that, if you consider the 3D region bounded by the four planes, the three coordinate planes and this plane. Then you get a 3D region having four faces, four triangles in fact. Which triangles? OAB, OBC, OCA, and the triangle ABC which lies in this plane x plus y plus z equal to 1. This oblique plane is x plus y plus z equal to 1. Coordinate planes you understand. So we give a special name to this 3D shape called tetrahedron. Tetrahedron. Okay. So basically it is this tetrahedron. Now, limits of x, y, z, you have to decide from this 3D region. This is very important. So how to decide limits? For z limits, choose a line through this region parallel to z-axis. Choose a line through this region parallel to z-axis. Okay. Your line enters through the base triangle OAB. The base triangle OAB lies in xy plane. So what is z here? 0. And it goes out of this triangle, but this triangle lies in this plane. So what is z here? 1 minus x minus y. From this equation you can write. Where the line enters through the base triangle where z equal to 0, goes out of this triangle ABC, which lies in the plane x plus y plus z equal to 1. So here z equal to 1 minus x minus y. So you can apply z limit 0 to 1 minus x minus y. So we are finding z limits. Draw a line parallel to z-axis through the region. See where it enters, where it leaves. Okay? Write those values of z. Now, how to find xy limits? For xy limits, project your 3D region into xy plane. What is the projection of this 3D region into xy plane? Can you imagine? In fact, this base triangle. In this base triangle, what is the variation of x and y? Now it is a 2D region, so you can apply the same approach as you did in double integrals. Either choose a line parallel to y-axis or parallel to x-axis. So let's choose a line parallel to y-axis. Where it enters, what is y on this line? This is x-axis, here y is 0. And where it leaves, parallel to y-axis, it leaves on this line. What is this line? The side AB. This line AB is the intersection of this plane and xy plane where z is 0. So what is the equation of this line? X plus y equal to 1. So what do we get? Y equal to 1 minus x. Clear? So y limits are from 0 to 1 minus x. X limits you can easily decide. Here x is 0 and to the rightmost point along the x-axis, x is 1. So x goes from 0 to 1. You understand the procedure now? Again I repeat, for z limits, draw a line parallel to z-axis through the region. See where it enters, where it leaves. Note down the values of z. Z varies from 0 to 1 minus x minus y. After that, project your 3D region into xy plane and then see the limits of xy in that projected region. Okay? That is similar to what you did in double integrals. So it should be easy for you. Okay? Now, these are limits of z. So what order you should write here? dz, these are 0 to 1 minus x are limits for y and dx. In this order, you need to solve this triple integral. Once you have limits, I have already explained in the procedure in the previous example for solving the triple integral. So you can apply that. First integrate it with respect to z, treating x and y constant. Then it reduces to a double integral in xy that you can solve. Finally, you will get this answer for this particular problem, 1 over 2 ln2 minus 5 over 16. This exercise you need to do yourself. The main explanation part I have already done, that if a 3D region is given, then how to decide limits for x, y, z. Okay? So verify this answer yourself. If you find something different, let me know. This example is fine. See the next example now. Find triple integral of z into x squared plus y squared dx dy dz over the 3D region given by x squared plus y squared less than equal to 1 and 2 less than z less than 3. First of all, do you understand this region? Are you able to make a rough sketch of it? What is x squared plus y squared equal to 1? It is an infinite cylinder that is cut off by these two planes, z equal to 2 and z equal to 3. So if you draw this region, make a vertical line. If you draw this region, what do you get? X-axis, y-axis, z-axis. It is infinite cylinder but cut off by two planes, z equal to 2 and z equal to 3. So this 3D region, okay, this is z equal to 2, means this circle lies in the plane z equal to 2, this is z equal to 3. So this infinite cylinder is cut off by these two planes. X squared plus y squared less than equal to 1 means the region inside the cylinder. Okay. Now again, limits of xy are not given to you. Limits of z are clear. Z varies from 2 to 3, but limits of xy not given. So what are limits of xy? If you project this 3D region into xy plane, what do you get? A circle. Which circle? X square plus y square less equal to 1. That comes here. Okay. In this circle, you can easily judge the limits of xy. If you choose your line parallel to y-axis, the limits of y are from minus square root of 1 minus x square to plus square root of 1 minus x square. And x limits are minus 1 to 1. But I don't want to do that. I want a simple procedure for doing it. Okay, because integration can create a problem. So here you can use substitution. Just like you did in double integrals, same way you can make substitution in triple integrals. Which substitution you can make? Let's choose x equal to r cos theta, y equal to r sin theta. And let's not change z, let's keep z equal to z. Do you recall, in this case r theta z are some special coordinates. I explained you in some earlier chapter. In chapter 13, do you recall it? What do you mean these coordinates? These are the relations between Cartesian coordinates x, y, z and r theta z. These are known as cylindrical coordinates. Okay, cylindrical coordinates. Okay, do I need to explain it? What are cylindrical coordinates? Okay, let me quickly tell you. Though I have explained it earlier, a point P is given in space. Cylindrical coordinate means draw a perpendicular on xy plane from P, that I am with a foot of perpendicular. Say this distance is r from origin to the foot of perpendicular. An angle of OM with positive x-axis is theta. Okay, this angle is theta. Then r theta z define cylindrical coordinates of the point P. You have done nothing, you have changed xy to polar coordinates. This point is in xy plane, so its polar coordinates are r theta. So r theta z together are known as cylindrical coordinates. These relations are trivial, you understand. By the way, in cylindrical coordinates, what are variations of r theta z? R can be anything greater than or equal to 0, theta 0 to 2 pi, and z, whatever limits are given to you. So z can vary from minus infinity to infinity. Okay, these are standard variations. Now in this particular problem, can you understand the variations of r theta z? R goes from this circle. R goes from 0 to 1, theta 0 to 2 pi, and z variation is already given to you, 2 to 3. Okay, so you can use cylindrical coordinates to solve this problem. So what can you write? This triple integral is equal to z remains as it is, x you are putting r cos theta, y r sin theta. So what do you get? R square. Yes, one more thing. What is dx dy dz? What is dx dy dz when you are using cylindrical coordinates? You know dx dy dz goes to Jacobian dr d theta dz. The thing is that what is Jacobian for these transformations? You can solve this determinant, it's simple. I told you for two variable case, apply the same thing. Partial x over partial r, partial x over partial theta, partial x over partial z. Likewise for y and z, you can write. Solve this determinant. you will get R. Okay, for cylindrical coordinates, you can remember it directly. The Jacobian is R. Okay, so dx dy dz goes to R dr d theta dz. If you're writing this order dr d theta dz, then put first the limits of R. These are 0 to 1, theta limits 0 to 2 pi, and z limits 2 to 3. Now it is a simple triple integral that you can solve yourself. I'm writing the answer for you. Verify it. The answer for this problem is 5 pi over 4. Okay? 5 pi over 4. And one more thing, sometimes it becomes mandatory to use the transformations. For example, here if I say I write something like 7 by 2, now you cannot solve it in Cartesian coordinates. It could be a problem, okay? So you should know the transformations, at least standard substitutions. Do you recall spherical coordinates? Because next problem that I am going to consider is based on spherical coordinates. Do you recall? Okay, let me remind you. How do you define spherical coordinates of a point in space? Say x, y, z are Cartesian coordinates for this point. How do you define spherical coordinates? Distance of the point from the origin is first spherical coordinate. We denote it usually by rho. Angle of OP with positive z-axis is phi. Okay. And if M is the foot of perpendicular of P on xy plane, then angle of OM with positive x-axis is the third spherical coordinate, that is theta. Okay. So what are spherical coordinates of this point? Rho phi theta. Rho phi theta. Do you also recall the variations of rho phi theta for xyz space? Rho is anything greater than or equal to 0, theta, phi, tell me about phi. Phi varies from 0 to pi and theta 0 to 2 pi. After that you should recall the relations between xyz and rho phi theta, very important. Easy way to remember it, rho cos theta, y is rho sin theta. You know these are polar coordinates. In this case, rho theta are polar coordinates for xy. When z is also there and you are dealing with spherical coordinates, multiplied by sin phi. Here, rho cos phi. You know when phi is pi by 2, you are in xy plane. So z becomes 0 and these are left as standard relations between xy plane and polar coordinates of each point in xy plane. Okay. So hope you recall these transformations as spherical coordinates. Now I am writing the problem for solution. Solve the triple integral x square plus y square plus z square whole power 3 dx dy dz. Where D is the region given by x square plus y square plus z square less than equal to 1. Do you understand this region? It is unit spherical region. The 3D region bounded by the unit sphere x square plus y square plus z square equal to 1. To solve this, you understand this? Unit sphere centered at origin, radius 1. So this all 3D region, okay? This is the region B that is given to you. Now, to solve this triple integral, it's good to use spherical coordinates. So put x equal to rho cos theta sin phi, y equal to rho sin theta sin phi, and z equal to rho cos phi. See what we get. You can check it, you will get here rho square whole power 3, and dx divided dz as usual goes to Jacobian d rho d phi d theta. d rho d phi d theta. Now the thing is that what is Jacobian for these transformations? You can solve it yourself using 3/3 determinant. We'll find it rho square sin phi. Either solve it or it is better you remember it. The Jacobian for spherical transformations, spherical coordinates is rho square sin phi. So dx divided dz goes to rho square sin phi. Then you can write the order. What would you like? D rho d phi d theta in this case. What are rho phi theta? Variation of rho phi theta for this unit sphere. Rho naturally goes from 0 to 1. First you have written d rho, so rho limits phi. Phi goes from 0 to pi, and theta is understood. Points are all around in the xy plane, so theta goes from 0 to 2 pi. After that it is a triple integral. All three limits are constants, so you can solve it yourself. Okay, first integrate with respect to rho, treating phi and theta constants, then integrate with respect to pi, treating theta constant, finally integrate with respect to theta. So after doing the calculations, you should get this answer. Verify it yourself. Okay. Alright, so you understand how to apply spherical coordinates. Using spherical coordinates, how to solve the triple integral. Remember that if I make it here, even in cube, if you go with Cartesian coordinates, it's a big problem. By the way, for this unit sphere, in Cartesian coordinates, what are the limits for x, y, z? In Cartesian, though we are not using those, but you should know. Draw a line through your region parallel to z-axis. See where it enters, where it leaves. It enters through the lower hemisphere below the xy plane. What is z here? What is z? Minus square root of 1 minus x square minus y square. Why? From the equation of sphere, x square plus y square plus z square equal to 1 means z has two values. Minus and other value is plus square root of 1 minus x square minus y square. So here you have this value. The line enters the 3D region, the unit sphere from the lower hemisphere and goes out of the upper hemisphere. So these values of z are fine, right? Now if you project this 3D sphere, 3D region into xy plane, what do you get? A circle. From lower side or upper side, both sides, the region is this circle. What is the equation of that circle? X squared plus y squared equal to 1. From this, you know the limits for xy. If you choose a line parallel to y-axis, y limits are minus root 1 minus x square to plus root 1 minus x square, and finally x limits are minus 1 to 1. So if you try to solve this integral using these limits, you will find yourself in a big problem. Okay? So it's better you know the uses of spherical coordinates. It's very important. Triple integral also provides you the volume of the 3D region, am I right? What is the formula for volume of the 3D region using triple integral? This is the formula, dx dy dz. xyz vary in the region D. Okay. In spherical coordinates, this formula transforms to dx dy dz goes to rho square sine phi. Okay. d rho d phi d theta. Alright. You can say it's a new region for rho phi theta. Now, if I ask you find the volume of the sphere x square plus y square plus z square equal to a square using triple integral. Answer you already know. Answer is 4 pi over 3 a cube. Is it? 4 pi over 3 a cube. But how to get it? Using this formula. You can use this formula for volume of sphere. The spherical coordinates is very easy to solve. What are limits for rho phi theta in this sphere? Rho goes from 0 to a, theta phi goes from 0 to pi, theta goes from 0 to 2 pi. dx dy dz, or you can write it directly in spherical coordinates you are dealing. So it is rho square sine phi d rho d phi d theta. Okay, you can solve it, you will get this answer. Okay. Let's do one more volume problem. Find the volume of the ellipsoid x minus 1 whole square over 5 plus y minus 2 whole square over 10 plus z minus 1 whole square over 6 equal to 1. This is ellipsoid centered at 1 to 1. How to find its value? It is the volume of ellipsoid. You can use a transformation to convert this ellipsoid into a sphere. What are those transformations? Let's use x minus 1 equal to root 5 into capital X, y minus 2 equal to root 10 into capital Y, and z minus 1 equal to root 6 into capital Z. So this thing changes to what? Capital X square plus capital Y square plus capital Z square equal to 1. You know it's a sphere. In the new coordinates, capital X, capital Y, capital Z. And its volume we can calculate using triple integral easily. Right? So these transformations are helpful, but once you use transformations, you know, okay, what is the volume formula? In general, triple integral dx dy dz. Okay, say the region enclosed by this is D. So over D you need to solve this triple integral. But after using these transformations, dx dy dz should go to Jacobian d capital X, d capital Y, d capital Z. Am I right? Can you tell me the Jacobian of these transformations? It's very simple. You have to write a 3 cross 3 determinant. Write partial derivatives of x with respect to capital X, capital Y, and capital Z. What do you get? Root 5, 0, 0. Likewise, write partial derivatives of small y with respect to capital X, capital Y, and capital Z. You get 0, root 10, 0. Similarly, for Z, you get 0, 0, root 6. D capital X, D capital Y, D capital Z. Solve it. See what you get. Simply product of the diagonal elements in the determinant. So you get 30 dx dy dz. So this changes to 30 times dx dy dz. But now the region of integration is the region inside the sphere. Okay. So for this region, again you can use spherical coordinates and solve it. Alright. So what is the volume of this sphere? Already you know. But you have to solve it using triple integral, okay? Using spherical coordinates. I'm just trying to write the answer. What is the volume of the sphere? 30 times volume of the sphere is 4 pi over 3. So final answer, the volume for this ellipsoid is 40 pi. Understood? So what we have done in this problem, we have first changed the ellipsoidal region into spherical region using these transformations. Once it's spherical region, we know we can use spherical coordinates and find its volume using triple integral. Okay? Alright, let's see one more problem on volume. Find volume of the cylinder x square plus y square equal to 1, z greater than equal to 0. You should understand the shape of the cylinder. Controlled by the sphere x square plus y square plus z square equal to 4. Find the volume of the cylinder controlled by this sphere. First, make a rough sketch of the given region, then we'll find its volume. It is infinite cylinder, but z is greater than equal to 0. What does that mean? Is the cylinder above z-axis only? Okay, is the cylinder above z-axis, but it is cut off by this sphere also. Cut off by this sphere. When it is cut off by the sphere's infinite cylinder above xy plane, you will get this kind of shape. Okay, tom kind of shape on the upper side. This is the sphere. You can say this is your sphere. Which sphere? This sphere. And this is your cylinder above xy plane. Fine. So we need the volume of this whole region. How can we do this problem? We can use spherical coordinates, cylindrical coordinates, and Cartesian coordinates as well. Okay, let's do this problem in two ways, using spherical coordinates and cylindrical coordinates. So first let's talk about spherical coordinates. If I want to find the volume of this region using spherical coordinates, how to do that? First we should understand in spherical coordinates there are three variables, rho, phi, theta. So for this whole region, what are the variations of rho, phi, theta? Rho is the distance of points from the origin. Okay, so the line starts from rho equal to 0, but goes out of the cylinder for this part, the part between these two circles, and goes out of the sphere for this part. It means we have to break the triple integration into two parts. For the part where this line goes out of the cylinder and for the part where this line goes out of this spherical part. Okay. So let's first focus on the case when the line starts from the origin, goes to the region, and then goes out of the cylindrical surface. So here rho equal to 0 certainly. What is rho when the line goes out of the cylindrical surface? What is cylindrical surface? See it carefully. Because once you decide the limits, after that you have to do calculation for a triple integral. So it's simple. So to solve this, you need to recall what is rho, what is x in spherical coordinates. Rho cos theta sin phi, y is rho sin theta sin phi, and z is rho cos phi. Okay, these are standard relations between x, y, z and rho phi theta. Okay. So if you do x square plus y square, what do you get? Rho square sin square phi. Here you get rho square sin square phi. From this, what is rho? 1 over sin phi, that you can say cosecant phi. So limits of rho for this region only. The region where the line goes out of the cylindrical surface. Rho varies from 0 to cosecant phi. Is it clear? Rho limits. What about phi limits? This is the uppermost point on the cylindrical surface. This is the bottommost point. So when your line is here, what is phi pi by 2? What is phi at this point? Means what is the angle of this line with positive z-axis. Can you find it? For this, first you need to find the plane where this circle lies. The circle is the intersection of the sphere and the cylinder. What is the intersection of these two? Can you tell me? It is z square equal to 3, means z equal to root 3. Clear? If I put x square plus y square equal to 1 here, z square is 3, z is root 3. So this plane is clearly z equal to root 3. This circle lies in the plane z equal to root 3. In general, at any point in spherical coordinates, z is rho cos phi. So you can say z equal to rho cos phi. At this particular point, z is root 3. I need phi, it means I need to supply the value of rho also at this particular point. So what is rho in this circle? This point lies on the sphere, right? And on the whole sphere, rho is 2. So you can say that this implies 2 times cos phi equal to root 3. Cos phi root 3 over 2, that means phi is pi by 6. Good. So at this point, phi is pi by 2. This point could be anywhere, okay, this side. And here, phi is pi by 2. So phi limits are also clear. Phi goes from, this is pi by 6. Pi by 6 to pi by 2. Is it okay? Theta limits, no problem. Points are all around. Theta goes from 0 to 2 pi. So when the line goes out of the cylindrical surface, these are the limits. If this line goes out of the spherical surface, then what is the relation of rho phi theta? This time it should be simple. Rho starts from 0, line leaves out of the spherical surface, so there rho is 2 clearly. Phi, here phi is 0, you know. Phi is 0 there. And at this point we have already calculated for covering this region. Phi is pi by 6. Theta limits again goes from, theta limits are from 0 to 2 pi. So you have two sets of limits to cover the whole region in spherical coordinates. So what should be volume? Required volume. You will write two triple integrals. One with this set of limits, other with this set of limits. So let's write them. Let's write these limits first. Rho 0 to 2, phi 0 to pi by 6, and theta 0 to 2 pi. dx dy dz in spherical coordinates goes to rho square sine phi d rho d phi d theta. Okay. So first integral I will return. Let me clean it so that we have more space to write. Second integral. This is for the part when the line goes out of the spherical top. Second integral is for the part when your line goes out of the cylindrical surface. So this time we will write rho goes from 0 to cosecant phi. This one. Phi pi by 6 to pi by 2, and theta 0 to 2 pi. Again, dx dy dz equals to rho square sine phi Jacobian into d rho d phi d theta. Clear? So if you want to find this volume using spherical coordinates, you have to break the integral into two parts. Because for rho, the line is going through two different surfaces when it goes out. It starts from origin, but when it goes out, for this part it is going out of the cylindrical surface, for this part it is going out of the spherical surface. That's why it is broken into two integrals. Alright, after this just you need to solve these two triple integrals and add those. I'm writing the answers for you. Verify. For the first integral you should get 8 pi over 3, 2 minus root 3. For the second triple integral you should get 2 pi root 3 over 3. Check these answers. Final answer should be 2 pi over 3 into 8 minus 3 root 3. Okay. This is the final answer. Verify it and let me know if you find some different answers. Okay. So this is the solution when you are using spherical coordinates. Now let's use cylindrical coordinates and see whether that is easy or this is easy. But in exam, if it is asked by spherical coordinates, you have to follow this only, no option. Second case, when you are using cylindrical coordinates. And cylindrical coordinates, what is the volume formula? Triple integral R dr d theta dz. This already you have to write according to the limits. Now, what are limits for r, theta and z in this region? For z limits, it's very simple. Draw a line through the region parallel to z axis where it enters. Where it enters. It enters through the lower base circle and goes out of the spherical surface. So what are z limits? On the spherical surface, what is z in cylindrical coordinates? It is r square plus z square equal to 4. It means z is square root of 4 minus x square. So z goes from 0 to square root of 4 minus x square. Is it fine? 4 minus r square, sorry. It is r square. 4 minus r square square root. These are z limits. And for r theta limits, you just project your region in the xy plane, you get this circle, and this circle is, for this circle, what are limits for r theta? Can you tell me? For this circle, what are limits for r theta? This circle, in fact, x square plus y square, what are limits for r theta? For this circle, r goes from 0 to 1, theta goes from 0 to 2 pi. These are standard, you know already. But also be careful. Now, first you have applied limits for z. That means it is z dz. Now it should be dz, dr, and d theta. Okay? You can solve this triple integral yourself and you will get the same answer. So this time life is easy. Only one triple integral. So it depends on the problem. You see, when you are using spherical coordinates, then you need to solve two different triple integrals. But in cylindrical coordinates, only one triple integral. Okay. So you need to practice more problems that will help you in a better understanding of this kind of problems. Okay. Let me take one more problem that is also related to volume. I am telling this problem just to explain you how to decide limits. Okay, so this is a different kind of problem. Find volume of the paraboloid z equal to x square plus y square cut out by the planes z equal to 1 and z equal to 2. First make a rough sketch of the given region. It is a paraboloid. You know the shape of this paraboloid. This kind of shape, okay? Infinite upper side. You need to find the volume of this paraboloid cut out by these two planes. So z equal to 1 cuts it in a circle. Z equal to 2 also cuts it in a circle. Let me show the planes also. These two planes, z equal to 1 and z equal to 2, or cutting this paraboloid into two circles. What is the equation of this circle? X square plus y square equal to 1. This circle x square plus y square equal to 2. Okay. Now you need to find this volume. Volume of the paraboloid cut off by these two planes. So how to find it? Which kind of coordinates are suitable in this case? Let's use cylindrical coordinates. Let's use cylindrical coordinates. So what is variation of r in this region, in this given region? Variation of r, can you tell? R starts from 0 but ends on this paraboloid surface. So if you are using cylindrical coordinates x r cos theta, y r sin theta, you get r square equal to z. It means your r goes from 0 to root z. Am I right? R goes from 0 to root z. Theta is clear. Points are all around the z axis. Theta goes from 0 to 2 pi. And z limits are clearly 1 to 2. So this is the volume. There's cylindrical coordinates, but you have to write Jacobian. What is Jacobian with cylindrical coordinates? R, and then for this order, dr, d theta, these are z limits, dz. So this is triple integral to get the volume of this paraboloid cut off by these two planes. First integrate with respect to r, treating theta and z constants. Then with respect to theta, finally with respect to z. So I hope you will do it yourself. Verify the answer. Answer is 3 pi over 2 for this particular problem. Okay, so with this, chapter 15 is over from my side. I have explained all topics given in that chapter. Now what you need to do, you need to practice more problems. Okay. Keep on practicing different types of problems, so that will give you confidence in solving the problems in the exam. Okay? Thank you.